Example 10.4. The 100 kHz square waveform of figure 10.32a is applied to the clock input of the flip-flop shown in figure 10.32b and c. If the Q output is initially 0, draw the Q output waveform in the two cases. Also, determine the frequency of the Q output in the two cases. Figure 10.32b, the clock has bubble, so it represents NGT, which is negative edge trigger. Since the J input is connected to Q bar and K input is connected to Q, the output will be 0 and 1 respectively. In the question state that the Q is initially 0. So, the K will start with 0 and the J will start with 1 since Q is opposite to Q bar. This red line is represent NGT and it is located at the second leading edge. In the two tables state that in order to get Q is 0, J must be 0 and K must be 1 and the Q we get is 0. When the J input is 0, K input is 1, Q output we get is 0 and Q bar is 1. And when the J input is 1, K input is 0, the Q output we'll get is 1 and Q bar is 0, and this process will continuous.
In figure 10.32c, the clock does not have any bubbles, so it represents PGT, which is positive edge trigger. Since the J input is connected to Q, the output will be 0, while the K input is connected to Q bar, the output will be 1. So, the J input will start with 0 and for the K input, we'll start with 1. By referring the truth table to get the Q output 0 and the Q bar is 1, the J input must be 0 and K input must be 1. So, the J input must start with 0 and the K input must start with 1. Let's illustrate the timing diagram. This is the way to illustrate the timing diagram. The red line is represent PGT because based on the flip-flop, there is no bubble, so we get the output for the PGT. Since the J input is 0 and K input is 1, it will produce Q output 0. And then for the Q bar is 1. And then for the J input is 1, K input is 0, it will get Q output 1 and Q bar is 0. And then the step will continuous. This is the Q output waveform in two cases. This is for NGT and this is for PGT waveform. And then for calculate the frequency of the Q output waveform in two cases is equal to half.
Okay, now let's calculate the frequency. Based on the statement, it was given 100 kHz of frequency. Because the output waveform in two cases is equal to half the frequency of the clock input, we will multiply it into half, and then we will get 50 kHz of frequency.
We have an 8-line to 3-line priority encoder circuit with D0, D1, D2, D3, D4, D5, D6, and D7 as the data input lines. The output bits are A, which is most significant bits, B and C, which is less significant bits. Higher order data bits have been assigned a higher priority, with D7 having the highest priority. If the data inputs and outputs are active when low, determine the logic status of output bits for the following logic status of data inputs. A. When all inputs are in logic 0 state. B. When D1 to D4 are in logic 1 state and D5 to D7 are in logic 0 state. And C. When D7 is in logic 0 state and the logic status of the other inputs is not known. From the question that was given, a priority encoder can be illustrated. And this figure shows an 8 to 3-bit priority encoder, which has 8 active low inputs that starts from D0 to D7 and provides a 3-bit code of the highest rank input at its output, which is A, B, and C. These priority encoders are available in standard IC form. The second figure shows the truth table for this question. The truth table, 0 indicates that it is high logic level. For 1, it indicates that it is low logic level. For X, it represents that it doesn't matter if it is high or low logic level. Okay, the first question asks for the logic status of output bits if all inputs are in logic 0 state, which is this one, are in logic 0 state. So, this is the truth table for this question. Okay, since all inputs are in logic 0 state, it implies that all inputs are active. Since D7 having the highest priority, which is 1, and all inputs and outputs are active when low, the output bits will be A equal to 0, B equal to 0, and C equal to 0. For the second question, it asks for the logic status of output bits if D1 to D4 are in logic 1 state, when D5 to D7 are in logic 0 state. Since D7 having the highest priority, as was stated from the question, we will focus more on inputs of D5 to D7. As input D5 to D7 are the ones that are active, which is having logic 0 state. Therefore, the output bits will be A equal to 0, B equal to 0, and C equal to 0. The last question asks for the logic status of output bits if the D7 is in logic 0 state and the logic status of output bits of the other input is not known. Okay, since D7 is active and having the highest priority, it will be encoded irrespective of the logic status of other inputs. Therefore, the output bits will be A equal to 0, B equal to 0, and C equal to 0. Okay, so this is the logic circuit for this equation, which has A is equal to D7 plus D5 plus D3 plus D1, and for B, A is equal to D7 plus D6 plus D3 plus D2, and for C is equal to D7 plus D6 plus D5 plus D4. This equation will be available from the truth table that was shown before.